Okay, now there was a homework assignment due tonight that was about to prove mutual exclusion, and the question was, how do you go about doing that? And here is some guidance on how to do that. If you go back to chapter 4, what we did is we proved the mutual exclusion of the third attempt. So this is your key one to look at. Notice this is algorithm 4.1, third attempt from chapter 4, and it has this Boolean want P initialized to false, want Q initialized to false. And basically what we did, let's see what we did. We introduced this notation that P3 ... means P3 or P4 or P5. Remember that? And then we had this lemma 4.3, and I think this is similar to, this always should be similar to what you're doing. A, P3 ... equivalence want P is invariant, and the proof is by mathematical induction on the states. The base case is the initial state. And then we did, here's the base case. We did this. The initial state is this. False or false or false equals false. 3.26, item potency, false equals false, which is true. And then we had the induction case, and we had to look. Here's what we had to do. We assumed that A is true in any state, and then we had to do by code inspection, and we had to prove that A is true in any subsequent state. And then we had to do a little code inspection, execution of which statements can change P3 ... equals want P. So we come up here and we look at this, and we see that it's statements P2 and P5. Remember that? And then, so here's the case P2, and then we did case P5, and we reasoned like this. And then we said similarly Q3 ... equals want Q is invariant. And now here's how you do, and then after you do those lemmas, here is the theorem that shows that that mutual exclusion is that we have mutual exclusion. We prove not P4 and Q4 is invariant. That is, algorithm 4.1 ensures mutual exclusion. And its proof is by mathematical induction. We do the base case starting at the initial, and then we do the induction case. Like that.
So you prove, when you're doing each of the lemmas, you do all of them by induction?
Mm-hmm. Yeah. So everybody, are you with me on that? So that's how you do those. That's how you.
And then when you say like, because when you start with the base case, say the initial state is like, for example, like P1, Q1, false, false.
Mm-hmm.
And then
I think yours has a turn in it also, right?
Yeah. So when like a statement, when like a P1 or one of those statements is false, that means it's not enabled. Correct. And when it's true, that means
No. Hold on. The P. Wait. Say that again.
Like go back a little bit.
Sure.
To 1.5.
Equivalence want P.
And that's P3 or P4 or P5.
This means P3 or P4 or P5, which in turn means P3 is the statement that will be executed next if that process is chosen, or P4 is the one that's going to be executed next if that process is chosen, or P5 up. Okay? So if you want to prove that in the base case, well, what you know, the initial state is P1, Q1, false, false. So therefore, P3 ... is false. But also want P is false. So we have false or false or false equals false.
But P3 is false because it cannot be executed next.
No. Oh, well, P3 is false because P1.
Okay.
Is it P3 saying that it's like the next step is P3 or?
Okay, yeah, good question. Yeah, no. Here's what P3 ... means. Now, so here it is. Here's what it means. P3 ... means if P is chosen to execute, P3 is the instruction which will be executed next. Or when P is chosen to be executed, P4 is the statement that will be executed next. Or if P is chosen to be executed, P5 is a statement that will be executed next. That's what that means. And it's because we have P1 is the statement that would be executed next when P is chosen, That means we have false or false or false or false. Are you with me on that? Yeah.
So if it was P2.5, it would be true, correct?
No, because it's
P2
P1.
But P2
Because it's P,
executed.
no. In the initial state, P1 is the next one to be executed if P is chosen. Are you with me? Yeah, I see what you're doing. You went one step ahead, but that's not the meaning of P3.5. Are you with me on that? Do you see what that means? Are we good? So, yeah, these are good questions, and this is the way you do that. All right, I'm glad we got that on the video. That was a good question. Okay, so these are ways to reason. This is how we reason mathematically about these properties of these for these algorithms. All right, now last time we introduced the concept of a monitor. Now, do you remember why? I mean, it seems to me like we have a perfectly good thing with semaphores. Why on earth do we want to do this complication with monitors? Now, do you remember what the purpose, why we wanted to, what advantage do monitors have over semaphores? Anybody? No, not necessarily efficiency. In fact, it might even be the other way around. Usually when you go to higher levels of abstraction, you sacrifice some efficiency, but not always. But no, wouldn't efficiency. Remember what it was? What's the advantage? This would make a good exam question, wouldn't it? What's the advantage of monitors over semaphores? Well, both semaphores and monitors solve the critical section problem so that there's no interleaving in the critical section. No, not necessarily one's more efficient than the other, because one's not necessarily more efficient than the other. But yeah.
Monitors are easier to program if you have a huge system where you
And
have to look at each individual process and compare every other.
Yes, that's what it is. Did you guys hear what he said? He said it's a programming advantage, because you don't have to have semaphores located. You don't have to analyze the system with semaphores located throughout all of your code. Instead, you put the critical sections in the monitor, and then you provide methods. You provide monitor methods for accessing the critical section. And that way the critical section, the code for the critical section is not all scattered throughout, maybe dozens or hundreds of files in the software system. Do you see what I mean? So it's a managing the program. It's a consolidation. It's a human advantage it's a human advantage for managing complexity. You see, it makes it simpler to put all the code into one monitor. So a monitor is like a class. In the same way that a class has methods and attributes, a monitor has things that are called condition variables and local variables, and also methods. And what do we know about, and what's guaranteed with those methods? The method of a monitor. What's guaranteed? The monitor guarantees what? No what? No interleaving in all of its methods. Its methods, you can consider its methods to be atomic. Are you with me? Is everybody clear on that? And then we looked at algorithm 7.1, which is how you would program our problem, that we use temp gets n gets temp plus 1. How you would program this with a monitor. What you do is you just make increment a method. And it's guaranteed to be atomic because it's a method in a monitor. Are you with me? Does everybody see how that worked? So now you don't do, notice that now there's no longer a wait S and signal S in the code, in the main program code. It's all, you just call this method, and then the method is guaranteed atomic. That comes automatically with the monitor. So let's see how Java implements monitors. The first point is that there is no special monitor type.
in Java. Instead, any class can be a monitor. And the key feature of a monitor is that the monitor methods are atomic. And the only thing you need to do in Java to make a method atomic is to put the keyword synchronized as a property of the method. So here in this next slide, we have the implementation of algorithm 7.1 in Java. And we have just created a public class named critical section, which is our monitor, and we have our private int n gets 0. And notice that int n does not need to be volatile now, because all the operations inside the monitor, all the methods of the monitor are guaranteed to be atomic. So here we have the critical section itself is a method named increment, and we have public synchronized void increment. And the word synchronized forces all of the statements in the method increment to be atomic, so that there is guaranteed to be no interleaving. So we have the usual int temp gets n, a little random delay to try to force some interleaving, but of course this will never happen as long as it's synchronized. And then n gets temp plus 1. And now we have one additional method named get, so that we can return the value of n from the monitor to print it out in the main program. So the next slide here shows our usual process ID that we use to distinguish between our two methods, between our two processes, because they both have to execute the same run method with the usual initializer to set the process ID for each process. And here's the common run, and we have our usual coding pattern: if process ID equals 1, and that's what process P executes, and then else if process ID equals 2, and then that's the code that process Q executes. And so now what is all we need to do in the run method is just to call the increment method from the critical section monitor. So we just do for int I gets 0, I less than 10, I plus plus. And in the body of the for statement, we just call cs.increment. And that guarantees that executes atomically. So there's the solution of the critical section problem using the concept of a monitor. And here is the main program. It's the usual initializing P and Q, giving P the process ID of 1 and giving Q the process ID of 2. But now we have a second parameter in our constructor, and that is we pass it the critical section, CS. And so in the main program, we first allocate a new critical section, and we name it CS, to match the name CS in our author's algorithm 7.1. And then we do the usual p.start, q.start, and the join. Okay, so let's see how C++ monitors are implemented. First, in the same way as Java, there is no special monitor type, so we have to actually write our own monitor class, in order to implement the monitors. And you construct a monitor using our usual binary mutex that we looked at in the semaphore chapter. But then we also have this auxiliary local variable named lockguard to make the operations atomic, and here's how it works. So here we have the class critical section that we have written to implement algorithm 7.1 from our textbook, with the usual int n initialized to 0. And it does not need to be volatile, again, because we are guaranteed that the increment and the get methods are going to be atomic. And now we have a mutex that we have named CS mutex, which is to guarantee that the mutual exclusion in the methods of the monitor. Now, here's how it works. Look at our void method increment. Instead of having the programmer write csmutex.lock at the beginning and then writing csmutex.unlock at the end, we use a local variable named guard to do the locking and the unlocking for us automatically. So guard is of type lock guard, which takes a parameter, a template parameter, in this case a mutex. And we are giving guard our CS mutex to lock and unlock for us automatically. This behavior is based on the fact that when a method is called, local variables are allocated on the runtime stack, and in the process of being allocated, their constructors get called. Furthermore, when a method returns to the caller and the local variables are deallocated from the runtime stack, and when they are deallocated from the runtime stack, the destructor for the local variable gets called. So a lock guard is programmed so that it will lock the mutex when it is allocated in the constructor, and then when it is deallocated from the runtime stack, the destructor will unlock the mutex. And so even though it doesn't look like we are locking and unlocking our CS mutex here, that is actually precisely what our guard does. And then here's our usual P run and Q run, and that's all we do is we have a loop that runs 10 times for each one of these processes, and it simply calls our cs.increment, which now is guaranteed to be atomic. And then we have our usual thread P, P run, and thread Q, Q run with P.join and Q.join. So in summary, here's how the behavior works. This pattern, this coding pattern, is called the C++ RAII design pattern. And RAII stands for Resource Acquisition is Initialization. And so the resource acquisition happens during initialization. In this particular code that we just looked at, the initialization happens when the method is called, and then the last point is that resource deallocation happens during destruction. And so in the case that we just looked at, when the local guard is deallocated, when we are returning from the called method, the destructor is the destructor is executed. So that deallocates our guard and unlocks the mutex. So here, these are the benefits of the C++ RAII design pattern. First of all, non-void functions would be difficult, if not impossible, to implement atomically with only mutex. Because think about it. If the function is not void, then we have to return something. But then how do you unlock after you return? If you unlock and then return, then interleaving could happen between the unlock and the return statement. So this RAII design pattern solves that problem by having the guard do the locking and unlocking for us automatically. And furthermore, RAII is exception safe, so if exceptions happen during the execution, if an exception happens during the execution of the code in the method of the monitor, then deallocation will happen automatically, and the mutex will be unlocked. And RAII simplifies resource management, and furthermore, it is most C++ libraries follow this RAII design pattern. So let's do a quick little demo here of algorithm 7.1 in C++. So here's our code. We've got class critical section. There's our int n initialized to 0, and there's our CS mutex, which is our mutex, and here's our guard for the and for making increment atomic, and the same thing for making get atomic. And here is the critical section. CS is a global variable, and so it's declared here on line 32. And so here's our P run, and here's our Q run, and here's our main. So it's going to be pretty boring because it's going to work. So here's the demo. And there we see the value of n is 20. We didn't have any interleaving. Let's see if we can get some interleaving in the output statements. Oh, there it happens. See, the value of n is still 20. Here you got a little interleaving up here on the output statements because they are outside the monitor. And so they got interleaved there at the beginning. All right, end of this short, sweet demo.
Okay, and then here we took a look at this picture, executing a monitor operation. And what the fact is that there's this these little stick figures represent processes. And the fact that there is one little stick figure in this box that is monitor CS means, the meaning of that is that only one process can be executing a monitor, only one process can be executing a monitor method at a time. And if anyone else tries to be executing it at the same time, they are blocked at the entrance, at the entry queue. Is everybody with me on that? Now, here comes something that is kind of hard to get your head around, wrap your head around. Excuse me. Monitors have these special variables. They are called condition variables. Now, normally when you talk about a variable, all variables have a type, right? So like you could have an int variable, you could have a real variable, you could have a double, and those are variables, right? Now, on the other hand, you could also have kind of like an object, which is an instantiation of a particular class. Yeah? And those objects, what does an object have? What does a class have? If an object has a type class, some class, what do all classes? Attributes and methods. Okay? Now here's what you should think of. Mentally, what you have to have in your mind is, you have to think, if I have a condition variable in a monitor, that condition variable has a queue of blocked processes. Now, can you visualize that? When you see condition variable in a monitor, what do you automatically think of? A whole bunch of a little waiting line, a little waiting list of processes that are waiting, that are blocked, and that are waiting on that condition variable. You have to visualize that? I think if you have that concrete picture, that'll help visualize what's going on. Okay, so a condition variable is a special monitor variable that has a queue. And furthermore, in monitors, the queues are FIFO. First in, first out, by definition of a monitor. Okay? A special monitor variable that has a queue, FIFO, of blocked processes. And furthermore, if you have more than one condition variable in the monitor, you can do that, and each one has a different queue of blocked processes. Yeah? Now, do you remember when we had that ready to run and running and blocked for input-output and blocked on the semaphore, waiting for the semaphore? And remember, each one of those things, they had like, we imagined that each one of those were queues of blocked processes. Well, this is the same thing. The monitor has its own little set of queues of blocked processes. Yeah? And however many condition variables you have, that's how many queues there are. So, anytime we have a class with attributes and methods, and we have an object that is that type, that has that class, what we ought, and when you program object-oriented programming, this is actually quite similar to object-oriented programming. And if you have an object, and you're used to doing code completion, like in NetBeans, and if you say my tree dot, and then what usually pops up? There's a bunch of what? Methods that you can call for that. Do you see? Are you with me? Okay. So, in the same way, there are methods that you can execute with a condition variable. Okay? And here they are. There's 3 of them. First of all, there's wait C. Now, why do we call it wait C? Because we want to distinguish this from what? What else had something that sounded like that? A semaphore has a wait operation. So we don't want to confuse this with the semaphore wait, so we're going to call it wait C, and wait C means wait condition variable. Are you with me? And furthermore, obviously, you guys, all of this stuff that happens with wait C, it's going to be guaranteed what? Guaranteed atomic. Yeah. And what does wait C do? So now, first of all, who executes a wait? A process does. Are you with me? A process does, executes the wait. All right? And that process, what does the process give to wait? What is the parameter in the wait? COND. And what is the COND? It is a what? A condition variable. So the process would say wait and give the name of a condition variable. Are you with me? And what happens? Automatically, what happens? That process P is appended to the what? To the condition queue. Now look, you guys, there's no ifs, ands, or buts about this. There it goes. It gets appended to the queue. And furthermore, the state of that process is now what? Blocked. And then the lock of the monitor is released. Now, what do we mean by the lock is released? Let's go back to this picture. As long as this process is in the monitor, these guys can't get in. But if this process executes a wait, there's another little queue over here to the side. It's not shown in this figure, but we'll show it in a minute. It will go into this blocked, this blocked queue, and it will unlock this so that another one of the processes can get in and be executing. Are you with me? So that's what that unlocked means. Okay? So does everybody see exactly what happens here? And this is all atomic. This whole thing is atomic. Right? So that's wait. And another one is called signal C. And again, we use the C to distinguish this signal C from the semaphore signal. But now this one has an if statement in it. Because you signal, so if a process signals a condition variable, what it does is if the condition variable is not equal to the what? To the empty set, the empty queue. Then what it does is it removes the head of the empty queue and it assigns it to Q, and then Q.state gets ready. All right? So that, are you with me? So when you signal, you say, oh, signal. Let someone else, let whoever's first in line in that queue be put in the ready state, so then it can run. All right? That's the second thing. And then the third thing is there's this Boolean. We're not actually going to use this very much, but you can if you want. Empty condition. So this returns whether or not the queue is empty. Right? So you can say, if you say empty, my condition variable, it'll say either be true or false. If empty, my condition variable, blah, blah, blah. And we'll test to see if that's empty and return true or false. Are you with me? Now, this next little table is not in the book, I think, but the concepts are all there. But here's a table to show what we want to do is we want to compare a semaphore with a binary monitor because a semaphore also has a wait and a signal, and a binary monitor has a wait C and a signal C. So we want to, you know how teachers like to do compare and contrast questions. Anyway, this is a little compare and contrast for us, just for your pleasure, your contemplation pleasure. So here we go. Let's do a little compare and contrast. What about a wait for a semaphore? If you say wait S for a semaphore, do you remember how does that work? Does the wait, what does the wait do? It does it add or subtract? It subtracts, but does it always subtract? If it's greater than 0, it subtracts, then it goes on, right? Otherwise, what does it do? If it's 0, then it blocks, yeah. So everybody understands weight S may or may not block. On the other hand, weight C on condition variable COND always blocks. Is everybody clear? Okay. Number 2, signal S always has an effect. Now what does signal S do?
Either adds one
It either adds 1, in which case it's doing something,
or it removes it from the queue.
or it removes it from the queue, in which case it does something. But signal C on condition has no effect if the condition queue is empty. So that's another slight difference. Are you with me on that? Okay. And there's one more. When we unblock a signal, when we unblock a process by executing signal S, where S is a semaphore, it may not resume execution immediately. But in a binary monitor, when signal C unblocks a process that's blocked on its queue of blocked processes, that one that got signals resumes executing immediately. This is called the immediate resumption requirement. And there's some really fine points here, some little detailed fine points, and we're going to explore this in more detail in a minute, later actually, okay? But, and we're going to contrast this binary monitor with other monitors, including the Java monitor, to see how things work in practice. All right? But for now, let's just note that with the semaphore, the process unblocked by signal S might not resume execution immediately. But now, I have set up here on the second column, this is a binary monitor. So binary presents a certain kind of monitor, and there are many different kinds of monitors. There are several different kinds of monitors. We're going to want to compare them. But with a binary monitor, the process unblocked by signal C condition resumes executing immediately. Now, we are going to go into a little bit more depth of monitors, a little bit more than what our author does. And I tell you, there is this great paper. It's written by Peter Boer and Michael Fortier. And the title of the paper is Monitor Classification. And this came out years ago, decades ago, in 1995. And in Computing Surveys. And man, when I saw this article, I thought, whoa, this is the definitive. And furthermore, I can tell that, I can tell that the author of our textbook has gotten some of his presentation ideas from this, because look, here is slide 7.8 from our author. It's called the immediate resumption requirement. And you see what our author shows here is the monitor in the middle, and one process is executing. And then we have, how many queues does it look like we have here? Plus the entrance. Are you with me? So 5 altogether. So there's a waiting queue, a signaling queue, an entrance queue, and then if we have 2 condition variables, there's a queue for each condition variables. And he draws the thing like this. And look, here's a picture taken directly from Boer's paper. Okay, and you have the monitor variables. Instead of having little stick figures, he's got little circles, and the solid dot there is the active task, and the ones and the open circles are the waiting tasks. So you see, this is it's a very nice way to visualize what's going on with monitors. And so this paper is available for you for download, and I think there's an assignment to study it. And what we're going to do today is we're going to go through the first part of that paper and show this classification scheme. Now, And what's really neat about this is that it systematizes and it's very systematic. Do you remember whenever we did sorting? Do you remember who came up with the sort taxonomy that we used always in data structures when we did all those sorting? It was Merritt, Susan Merritt. She was the one who came up with what does every sort, pairwise comparison sort do generally? Split, sort the sub, join, boom. And you can classify all the sortings according to that taxonomy. So Boer did the same thing with monitors. You see what I mean? This is a classification. It's a way to see, just a way to compare, see what the differences are between these different monitors. And it was extremely systematic. And not only did he take the literature and take all the practice, and he synthesized this whole thing. And not only that, the second half of the paper, which we're not going to cover, he actually does proofs of correctness and shows how difficult the proofs of correctness is for each of these monitors. And then he also does the simulations to show performance. So he does performance analysis. It's just really, I really like this paper. It's just really good. And I think it will serve us well. Okay, so now, in the same way then that we have a general way to do sorts, there is a general way to have monitors. And by the way, the reason we're going through all this is because, unfortunately, there is no standard monitor. It seems like every programming language and every library that provides a monitor provides a different kind. They are kind of like different from each other. So there's no standard. You see what I mean? We can't say, And so I don't want to leave you with the impression that the monitor that we learn in binary is the way all monitors work, because it's not. There is no standard. They all differ from each other. And one of the things that we're going to look at is how Java monitors work. Okay, and so it's a really helpful compare and contrast way to do compare and contrast. So here's what a general monitor does. First of all procedures are mutually exclusive. Okay, so we know that from the monitor that we looked at in binary. Okay, all procedures are mutually. What does that mean? Mutually exclusive. Only.
Happen at the same time.
Yes, only one process. Only one process can be executing any of the methods at one time. So they're not running concurrently in the monitor. In the monitor, only one. So the monitor enforces mutual exclusion. That's guaranteed. That's a property. That's guaranteed. That's given. Okay? And furthermore, each monitor has a bunch of queues. One queue is an entry queue. Now, what do you suppose we mean by an entry queue? Because what can you do? What operation can a process do in a monitor? If you have a condition variable, what can you do? Well, I take that. I didn't ask that very well. What does a monitor provide? What if you program up, if you use a monitor in your program and you construct a monitor, what do you write? What do you allocate and what do you write? With any class, what do you allocate? What do you write? You allocate attributes, yeah, attributes and methods, right? So you've got, and some of those attributes, they could be integers, they could be doubles, whatever. They could be condition variables. Are you with me? And anytime and then you write a method, you write a procedure, okay? And so the entry queue is when the process is wanting to execute one of your methods. They might be stuck at an entry queue. In the entry queue, why? Because someone else is executing one of those methods. Do you see what I mean? So that's the entry queue. All right? Now, the second kind of queue that a general monitor has is it has one queue for each condition variable. Okay? We've already seen we've already seen an example of that. But now the one thing that we didn't look at before, we didn't kind of consider before, is in general, there is also one waiting queue and one signaler queue. Now, why do you suppose there's a waiting queue and a signaler queue? Because what are the two basic operations that we can do on a condition variable? We can execute what? Wait C and signal C. So because a process, while it's executing code in one of the methods of the monitor, because it can execute a wait C and because it can execute a signal C, there is a waiting queue for the processes that have executed wait C, and there is a signaler queue for the processes that have executed signal Q. Signal C. Are you with me? Okay, so look. So here is the picture. Figure 3 this is figure 3 from the paper. All right? And so let's take a look. Now see, he has his entry queue. They're all lined up here. They're not just kind of jumbled, but they're in a line, right? And so that's the door to get into the monitor. And there's a bunch of monitor variables here. And here there is an active task. And here he has another little door down here called exit. So whenever a process finishes executing one of the methods in the monitor, then it leaves, and then there's room in here then. And furthermore, when there's room in here, what does the monitor have to decide? Does the monitor have to decide once one of these guys exits? What does the monitor have to decide? Which queue to take it from? Who's going to get in next? Well, no, there are just these queues. But the monitor software, the monitor specification has to decide there has to be a protocol, or there is a protocol. And depending on what kind of monitor it is, the monitor will take it from one queue or another queue.
Does the active task have to signal before it exits?
There's no requirement that it does anything. The programmer can program it however he or she wants to program it.
Okay.
But in order to have things work smoothly, you should program it, signals and your signal Cs and your wait Cs, so that everything works well, everything runs right. Okay, so does everybody see? So and there's always one active task, and then there could be these waiting tasks in any one of these queues. And now look at here. Remember what we said that is a requirement for the monitor queues? They have to be what? First in, first out. And do you see how this shows that? Because look, if this guy executes a wait, then this guy is going to come in here and wait. And where is he going to go? Suppose he does wait on condition A. Where is he going to go? He's going to go in this door, you see, and then be in the back of the line for whoever can come out, back of the line of. Do you see how this kind of like shows you that it's FIFO? Do you see what I mean? Because they go in the back here and they have to get in the back of the line, first in, first out. So I think I like this way of showing the FIFO. Is everybody clear on that? Okay, now here's what happens. And now this is in general. This is completely general so far. These are the general actions. Okay, when wait C is executed, you give it a condition variable, right? You say wait C and you give it a condition variable. When this executes, that process who executed wait C is blocked on the condition queue for COND. Are you with me? So here, this guy's executing. He'll go into this queue, this condition queue. If he does a wait CA, he'll go into this queue. If he does wait CB, he'll go into this queue. Yeah? Excuse me. Now, and here's what signal C does. When signal C executes, the signaler, now what do we mean by the signaler? The process that does what? That executes the signal C. And which process is that? That's that little black dot in the middle. It's the one that's executing code. Yeah? The signaler is moved to the signaler queue. Now where's the signaler queue? That's this one, the lower right here. Okay? So boom, he executes signal. Boom, he goes into this queue right here. Are you with me? He goes into that signal. And the signaled is moved from the condition queue to the wait queue. So now what, because when you say signal condition, what are you specifying? You're specifying one of these what? You're specifying one of these queues. Do you see what I mean? So he goes, so the signaler goes to the signaler queue, and whichever one he signals, that one goes into this waiting queue. The first one here goes into the waiting queue. All right? And furthermore, at that point, because the signaler and the signaled have both been moved to the queues, now what do we have? Now what do we have? What situation do we have? We have room in the monitor. Okay? We have room in the monitor to, and the question is, which one is going to be picked to run? Okay, so the monitor is unlocked, and the monitor chooses from one of the queues which process gets to enter. Now, does everybody see that this is the general, this is what happens in general? Are you with me? So just imagine those actions. I think we might even have some, actually here it is visually. Okay? So watch this. Here it is visually. The action of wait C. So who is executing this wait C? A, condition variable A. It's this process that's this black one that's in the middle, right? It executes wait CA, and so what happens? Process is blocked on condition QA. So this guy goes into here. Are you with me? The monitor is unlocked, and an unblocked process is selected to continue. So does everybody see that? This, when you do signal, this goes into here and then unlocked, and one has to be picked. And we got several different choices, We could pick from this queue, we could pick from this queue, from this queue, from this queue, we could pick from whatever, all right? And here's the action of signal C. So look, this guy, so the signaler goes to the signaler queue, boom, so there he goes to here. If he signaled A, then the signaled goes, the first one in condition QA, in the queue for condition variable A, goes to the waiting queue, the monitor is unlocked, and an unblocked process is selected to continue. So does everybody see that that's what happens in general? Yeah, question?
Are the tasks in the signaler queue unblocked?
Ask me that again.
Are the tasks in the signaler queue unblocked?
They are all the ones in the, all of the processes in all of the queues are always blocked. All of the processes in all of the queues are always blocked. And what happens is, when a wait is executed, that causes the process that executed wait to block, and when signal C is executed, it causes everything is all still blocked. But once everything is all still blocked, at that point, the monitor has to pick which one to unblock to then be able to be the single thread that's executing a method in the monitor, a monitor method. Now, does that answer your question?
I think so, but when it's picking, it can pick anything except for conditions?
No, it can pick, what I'm saying is now, depending on what kind of a monitor it is, it will pick one thing over another thing. Do you see what I mean? But in general, this is what happens. This is what happens in general. And it can pick, you could design a monitor, there are some crazy monitors that pick one thing and some that pick, and we're going to see that's how one monitor differs from another, is how the choice is made as to what gets picked when everything has been, when the signal happens or when the wait happens and everything is all blocked. Then the kind of monitor it is dependent on how it makes the decision as to which one to pick next from all those blocked queues, all those queues with all those ones being blocked. Yeah.
I think that kind of answered this, but I'm so confused. If all of the queues are blocked, how does it pick an unblocked
It can unblock. The software can choose which one, in the same way that the scheduler in an operating system can pick which one to run. The software in a monitor can pick which one to unblock and therefore give control and be in the middle, be the thread that's operating a method in the monitor. Is everybody, are you with me? These are good questions. Let's make sure we get the ground, we understand what's happening in the ground, you know. Are we good? Okay.